Welcome to this AI Product-a-thon session organized by Feedback First about building an article recommendation engine from scratch. So Feedback First is a program which is a personalized mentoring program where you get to build AI products from scratch which solve real-world problems. Right? And one of the products that our students have built over the last couple of years has been this article recommendation engine, which has become quite popular and which is probably the need of the hour with respect to lots and lots of good data that we are surrounded with respect to articles, with respect to videos, tutorials, everything. How can you build your own article recommendation engine that will help you discover interesting insight and patterns, right? So that's exactly what we're going to see. So before moving ahead and then showing how to build this, the first question that whenever you're building any AI product, what you need to look at is who are you building it for? And you need to have answer these three questions before you move forward with any AI product, right? Other than, not just article recommendation engine, any AI product out there. The first question is, who needs article recommendation engine? Who are those end users who are going to actually interact with your article recommendation engine? Is it you? Are you building it for yourself? Are you building it for probably data scientists? Are you building it for product managers? Are you building it for maybe like first class, first standard, second standard kids? Are you building it for working professionals in a particular domain, right? Who are you building it for? So you need to have that clear. So the article recommendation engine that I'm going to show you is actually built for data scientists, right? So in order for them to actually get access to real world case studies, that's what our students would be using. And that's exactly what we have chosen. And then the next question that you need to ask is, how will a perfect article recommendation engine look like? What exactly are people looking for when it comes to consuming these real world case studies? As a data scientist, I want to be exposed to real world case studies about a topic of my choice. Let us say I'm interested in NLP related problems. How is Uber using NLP to solve their real world problems? How is Swiggy using NLP, right, to solve their own review analysis problems? Right. The moment I read about Swiggy, how they are analyzing user customer reviews using NLP, I would also like to understand related articles which talk about probably Amazon using NLP techniques, or maybe some research papers on NLP, particularly for sentiment analysis. Right? So those are the things that we are typically looking for when you are building this recommendation engine. Right? And then the next and the final step is, where do you get this data? Right, so how do you actually get this necessary data? Right, so from where exactly you get this data? So when we build this article recommendation engine, the data scientists actually got this data from a variety of good sources out there. You have Towards Data Science, you have Medium, you have GitHub, which contains these case studies, Netflix engineering blog, Uber engineering blog. There was a collection of these articles, close to 200 articles that were shared in one GitHub repository. I'll also be providing the link to that GitHub repository a bit later, right? And from there, we just scrape the data and build this recommendation engine, right? So now, once you have these questions clarified, the next step is to build the recommendation engine pipelines. How do you go about building this? Right? The first thing that you do is collect the data. So in our scenario, we collected the data from social media platforms like LinkedIn, GitHub. You have people going to respective companies' engineering blogs and then collecting articles from there. And once you collected the articles, now the next step is, how do you analyze these articles, right? You just have the URLs of these companies, of these articles that you have, right? And how exactly are you going to analyze the content if you're not getting the content from the article? You have the URL, right? Using the URL, what we did was we scraped the data, right? So we cleaned data. We actually used Python to actually do this. So using Beautiful Soup package, we actually cleaned the data, right? And we made sure that the content, the most important content in the article is collected, right? We use Python to do that. And then once we scrape the data, the next step is to actually summarize it. Because generally what happens is you have a URL, it will contain not just the text, it will also contain a lot of unnecessary information, right? A lot of images, references, and all that. So we can actually build models which also analyze images and all that. But for the first cut, we wanted to keep this thing simple. And so what we did was we used transformers, pre-trained transformer models, which were quite powerful, to perform something called abstractive summarization. which means generally traditional summarization is called extractive summarization, where you are just choosing the most important sentences in a paragraph, and then you're just removing everything else. Right? You are ranking the sentences in a huge paragraph, and you're just maybe let us say paragraph contains 20 sentences. You'll be choosing top 3 or 4 sentences. That is not that powerful. Right? Extractive summarization doesn't really capture the essence of what the paragraph is trying to say. On the other hand, if you have abstractive summarization, if you use these pre-trained transformer models, which were trained on huge corpuses like Wikipedia corpus, newspaper, news articles corpus, right? Then the advantage that you have with abstractive summarization is it will actually paraphrase sentence. It is not going to pick and choose sentences from the paragraph. It is going to understand how different entities in that paragraph are related to each other, and it is going to summarize it. An example would be, right, instead of choosing 3 sentences from a paragraph containing 30 sentences, it might just summarize it using, summarize even a 40-sentence paragraph into 2 sentences. But these 2 sentences might not be there in the paragraph itself. Right? It is going to summarize it using its own understanding of that paragraph. We'll also see how that actually looks like. Right? And then the next step, once you generate the summary, now this summary is going to be the input to the model. Right? So we're going to actually create features out of this summary, because we want to see, based on the summary of an article of, let us say, Uber's customer review analysis. Right? I just took the review. Now I've generated a summary from this article. Which other articles' summaries are similar to this summary? Right? That's exactly what we are trying to find out with this recommendation model. Right? In order to do that, what we did is we used word-to-vec as our embedding feature engineering technique. That's where we focused on making sure that we are trying to get a sense of the summary. Right? We actually trained the model. We built the word-to-vec models to kind of understand how exactly this summary can be vectorized. Right? We generated word vectors for sentence vectors for the summary aspect of it. And once we had the word-to-vec vectors in place, the next step was to build a simple recommendation engine. We started with cosine similarity. Right? So what cosine similarity does is cos theta. You might have heard about it during your trigonometry days. Right? If cos theta is 0, that means if cos value is 0, that means both of them are orthogonal. They're completely independent of each other. 2 reviews, right? If you're calculating the dot product, if the value is 0, that means those 2 reviews are not similar, right? When will cos value be 1? When both of them are aligned, right? When cos value is 0, which means, right? So when both the summary reviews, both the word vectors, if you multiply them, if you are getting the value as 1, that means they are as similar as possible, right? So what we did was we took these word vectors for all these 200 to 250 articles, and then we calculated the dot products across all these combinations. For every incoming, any article that you choose from the user, you are going to actually calculate the cosine similarity with respect to all the other articles in the database and pick the top 2 or 3, which have the highest dot product. And that's exactly how you're going to get related recommendations, right? And then once you got the recommendations, once you build the model, the next step is to push your recommendation data into the database. The database that we used was MongoDB. And MongoDB was very simple. If you think of it, you can easily get started on it. It's a NoSQL database, which means in future, if I want to add more stuff to my output, right now I'm just taking the URL and the name of the article as the things that you show when you are looking at the recommendation. Right? But in future, if I want to show something else, if I want to add probably the company logo, company name and all that, NoSQL, it being NoSQL database, becomes easy for us to actually make those modifications. Right? And then the cycle repeats. And how we deployed this, I'm going to actually show you how the mobile app actually worked out. Right? So if I just come here, right? So this is how it actually looks like. If you look at our mobile app, right? So this is aiquotient.glideapp.io, this mobile app. And if you come to the case studies part here, you click on a case study. Let us say I click on this particular case study, the technology behind fighting harassment on LinkedIn, right? And as you can see, you have all these different details about the company name, article, review, and everything. And then if I just scroll down, right, you will see the most similar article, right? And then you'll also see the second most similar article, right? And then you're also going to see the third most similar article, right? And as you can see, because we're talking about harassment, you're also looking at enhancing integrity. You have one recommendation on that, right? And because you're talking about the technology behind social media platform like LinkedIn, right? You're also getting information about democratizing data on this, right? And these recommendations are pulled from the database directly. That's for this mobile app, right? You're having this information is getting pushed to the database, and whenever this particular recommendation is selected, right, it is pulling all those recommendations that are similar to this, which were calculated in this step, right? So like that, what we have done is whenever a new article is uploaded, that's what we are going to, I'm also going to show you exactly how the articles are getting uploaded. All I need to do is I need to give the article name, article URL, and if you want to give article summary, you can give. But generally, even if you don't give, the machine learning transfer model will automatically generate the summary. And then you mention the topic, you just share it with everybody, and this goes to the pipeline. Right, that article will be cleaned, content will be scrapped, right? And then you're also going to look at summarizing. The summary will be generated, and feature engineering is going to happen, right? And then finally, the quotient similarity model is going to be built. You're going to push the information to the database, and then finally, the cycle will repeat, right? So this is how the entire recommendation engine pipeline looks like, right? But then the big challenge is building recommendation engine is one thing, but evaluating the recommendation engine is a harder thing because this is all unsupervised. There is no output variable. I don't know in advance which articles will people like, which articles are actually loved by people. And how do I know this recommendation engine is good? Same problem exists for YouTube, Netflix, and everybody. Right? Even YouTube and Netflix, you don't really rate videos, right? And they're also not showing videos by ratings. Okay, so basically that's where the recommendation engine differs from other AI products like anomaly detectors, predictive models, and other stuff. Right? The way this is different is you are more interested in how the users interact with the recommendation engine in order to understand whether the recommendation is working or not, rather than using any vanity metrics. Like you can look at some unsupervised metrics like Duns index and other stuff. Like you can look at probably even RMSE, F1 score, precision recall, and all that, but those do not hold any value in real world. That's what we did was we wanted to capture the user interactions, right? The clicks, the bookmarks. Like we also provided a functionality in the app where they can actually bookmark the article, right? And also the browsing history. In what order are they looking at recommendations? Are they clicking on the first recommendation or are they clicking on the third recommendation? If on an average, we see that in this app, right, we are seeing majority of the people actually clicking the third recommendation more than the first two recommendations, which tells us that probably we need to tweak our recommendation engines. Probably we need to look at a different embedding technique. Probably we need to look at maybe removing some noise in the scraping side of things. Maybe we need to generate a better summary. Right? So we tried different experiments and we found that out of all the different embeddings that we've used, compared to even transformers and Glow, Word2Vec gave us the best results compared to any other embedding out there. We started with the transformer embedding, and then we started looking at Glow and others to actually get the features rightly aligned. Right? And then we also tried calculating Euclidean distance and Manhattan to start with. But then both of them suffered from curse of dimensionality because there's just so many dimensions. We went with 300 dimension word vectors, and that's the reason why cosine similarity finally worked for us. Right, but you need to tweak it based on your data. It actually changes the whole pipeline. But the pipeline will remain the same. But the most important part is you need to take the feedback, right? And how we actually collected the feedback was we decided that an user is liking the article when he's actually bookmarking it, or when he is actually clicking on it and actually reading the article. Right? So we use simple browser side, client side JavaScripting to kind of capture that interaction and the information, right? And the other thing that we also looked at is we performed an A/B testing. So initially we started with, we did clustering based recommendations, and then we started looking at collaborative filtering techniques, and then we stumbled on cosine similarity, and we saw that when we did A/B testing, we got more engagement, more clicks when we use cosine similarity powered recommendations than clustering recommendations. That's another thing that we learned during this process. And the most important part that we also learned based on feedback is whenever you're building this article recommendation engine, you have to keep things simple, right? The moment you complicate things, let us say the user doesn't know why a particular recommendation is shown to him, right? Then it becomes hard for him to actually trust your recommendation, right? And that's exactly the challenge that we had. So whenever we were showing recommendations, we are now working on trying to tell them. So right now it's a work in progress. We are trying to now tell the user as to why this particular recommendation is shown, right? Because he has seen so-and-so recommendations. Initially, we start with randomly showing him 3 topics, 3 related articles, just like what Netflix does. When you're signing up, it will ask you to choose 3 topics. Right? Similarly, we ask the user 3 topics that he's interested in: machine learning, deep learning, and statistics. Based on his choice, we actually show certain articles. And once he starts clicking on them, we'll start showing related articles. Right? So that's exactly what we have done. And another thing that we also done is capturing the user clicks interest. It becomes even more easy when you are having a web-based application. So right now I just showed you mobile app, right? But because the backend is the same, we also used the same logic to actually also tweak the web application, right? So if I just if I come to this is the new version of the website, feedbackfirst.app. But if I just come here, article recommendation engine, if I just click on that, right, I'll be directed to the articles side of things, where I see these are the articles that are being recommended for this particular user, right? So I have these articles based on his interests that were shown, and these are the articles that I also favorited out, right? So these are the things that based on these favorites and the previous clicks, right? I'm actually looking at this, and I can just click on an article, right? I'll be directed to that respective article where I can actually look at that information, and I can also give feedback, right? If I love the article, I'll just bookmark it, right? And that way, the recommendation engine will be constantly optimized, and it will update the recommendations in the backend database, right? So this is how we have built this article recommendation engine, and still there's a long way to grow. It's just like, if you think of it, it is just the first version of the article recommendation engine, and depending on the content, depending on the sources, we're also trying to make sure that this is scalable. That's right now the initial set of data that we have came from crowdsourcing, basically different students trying to share the articles that they're coming up with, the mentors validating that, and then trying to update the database based on that. But in future, we want to automate this flow, and that's another thing. That's a thing for another day. Probably in a subsequent session, we can actually look at that, right? And so finally, this is what we wanted to cover as part of this. If you have any questions, feel free to ask, right? And I'll be more than happy to explain if you have any queries on this.